In this video, so through understanding Hooke's law, we're going to try to tie in elastic potential energy and simple harmonic motion. So to give you that introduction, very often it's done if you're ever studying, for example, waves. Now, if you want a little bit of a further study on Hooke's law, I'll put up a link up above there for you in terms of that introduction. So in here, okay, I won't spend too much time, although you do have to understand what Hooke's law is all about. Now, just a quick recall with regards to Hooke's law. So within here, as you can see there on the screen, so it states that if you take a spring, so it's the springs as you see, for example, within here, that particular spring, if the force is proportional in the spring to the spring's displacement, then we can apply Hooke's law. And then the definition of Hooke's law in terms of a formula is that the force in the spring is equal to negative K. So the negative is a restorative force that we have. The K is a constant that we would have that is dependent on the spring, so how the spring is made. And then the delta X is actually the displacement. So it's technically like a delta D that we have, but we'll use X. Now, what do we mean by the force being proportional to the spring's displacement? Well, so here, if you jump in and you look at these figures, and you have, so for example, there is some mass, okay, which is attached to this particular spring. And now if we take that mass, and let's say that we would stretch this out. So we would be under this constraint within here. So we took that mass and then we stretched out. So we stretched out the spring. Now, you know that if you're going to be taking in and you have a stretching force, okay, that is in this direction, then the spring itself will want to restore itself back to its original shape. So it's going to apply an opposite and equal force, okay, to the stretch that you've caused. And that's exactly what this force is all about. So this particular force, this negative, just means it's in the opposite direction. So it is always in the opposite direction of the displacement. So if you displace it, so if this is 0, and you now start to displace it, so this would have been delta X. So if you displace it in the positive, well, then the force is going to be in the negative, so meaning in the opposite direction. Now, if you do the same thing and you compress, so if you compress a spring, it will want to kind of reload back, okay? So it's going to want to try to restore itself again to this position. So it's going to be now pushing, okay, instead of pulling in this direction. So if you're pushing this in this direction, it's going to be pushing back, but in the opposite direction. And again, it would have this particular constraint within here. So the direction is always opposite to the displacement, and we call it a restorative force. It is always proportional to the spring's displacement. So, you know, if this is not very much, if the displacement within here is very small, then the force proportionally will be very small. If you try to stretch it out, you know, further, then the force proportionally will be bigger, okay, depending on the displacement. And the same thing happens on this side where you're compressing. If you compress it very little, not a lot of force will be kind of pushed back by the spring. If you compress it a lot, then the spring wants to get back in, so it will proportionally, okay, apply an equivalent force. And that's what Hooke's law is all about. Now, it does deal, okay, in the sense of ideal springs. So this is a constant, okay, so this K is related to the spring, so how it's kind of manufactured or made or whatever material that it is, it has a particular constant of how much stiffness it has and how much ability of pushing back and restoring the force back in. And it is always in newtons per meters if it is in metric standard units. Now, the ideal spring, so the word ideal spring, means that it has no internal or external friction. It basically obeys this law. So there isn't any friction that you have, okay, internally. So there isn't really an energy transfer, okay, that might transfer to heat or some other ones. It just gets stored up in the spring. Now, this storing up of the energy as you kind of take it and stretch it, so that means now you're storing energy within here so it can coil back. If you're compressing it, so again, you're giving it energy, and that energy gets stored back in so that it can coil back and push out. So that concept of energy is now known as elastic potential energy. So the word elastic within here means that it is energy that is stored and due to either a stretch or a compression in any of a material. So we think of it as springs because it's easy for us to kind of think of a compression and stretch of springs, but it can be any material. It could be elastic bands or anything of that nature, something that is capable of stretching or compressing. And then what you're doing is you're storing within the bonds of that material now energy, which would be a potential energy, which might get released so that it can coil back, okay, or stretch back to its normal size. Now, that elastic potential energy for these concepts of springs that obey Hooke's law is actually equivalent, okay, to 1/2 times the constant of the spring multiplied by the displacement that you have squared. Now, where in the world does this come from, you might ask, and that's a great question. So if we take this, and I'm going to draw out, and this is going to be drawing out, this is the amount of force that we have in the spring. So that is our force right here. So this is what I am referring to. So what is the amount of force that we have in the spring, dependent on the actual displacement that we have. So this is like your delta x, okay? So how much are you displacing it? And our displacement right here, so this would be no displacement at all, so this would have been 0. And in here, you're stretching out the spring, okay, as you're going in this direction. So you're stretching out the spring, so it will want to coil back. And then in this direction, so if you're pushing in this direction, so this is like you're compressing this actual string that you have. So meaning you have these two instances. So if I take this one, this is the compression, right, away, okay, so from, so if I would align it within here, so this would have been compressed in here that we have. And then on the other side, so if I would take this one right here, I'm going to just steal that and bring it within here. So that would have been, now I'm going to overlap them, okay, so that you can kind of see that within. So if I now overlap and it stretches back out, all right, so this is what it would be. Okay, so this is now a stretched one, and this particular stretch right here would have been stretched on this side. So this is positive, this is negative, so this is compression, this is the stretch. And now what happens due to Hooke's law, because we know that this right here is equivalent to negative K, and K is again a property of the spring times the displacement that we have, so it's proportional to the displacement. And therefore, so what you would see is, so this particular negative, and this is now related back in, if you recall, y is equal to mx plus b, which is your line, right, equation, where y is equal to the spring force, the b, which is your intercept, so this is really 0, and then your m is the slope, and our slope is the negative k, so therefore it's sloping with a negative k. So what this would be, this would look something like this, right? So this is what you would have within here. It's a negative k, so this slope right here, and that particular slope is equal to negative k value. Now, what this is saying is that the actual force that the spring, so the restorative force that it has, now when it's on the negative side, it just means that it's to the left, right? Okay, so that's what happens there. And therefore, so if it's here, it's very small, okay, it's trying to pull back. Well, you keep making the spring and you pull it or stretch it more and more, the proportional spring will give more and more force as it will try to coil back in. And then on the other side, if you compress a little bit, not a lot of force, but if you keep compressing, more and more force happens. Now, by the way, in the real world, these types of springs or materials, the actual Hooke's law, it's not like it obeys Hooke's law everywhere, right? So eventually you might break the spring, or you might break the material. It might be an elastic material, it might just simply break. It can only stretch so far. And into the extremes, it may not exactly obey Hooke's law, but around the boundary, it certainly does. So around some boundary, okay, within some delta x, it follows Hooke's law very nicely, right? So this is kind of on the assumption that it's an ideal spring material. So now, why did I show you all of this, and why did I show you this graph? So this graph should be understandable for you in terms of what the actual force would be related to the slope, which is just this negative k that we have from Hooke's law. Well, so how does this relate it back to the amount of elastic energy? Now, that's going to take you a little bit step backwards. So what I would want you to think back, okay, if you think back of work, how exactly was work defined, right? And then how do we find what work is? So the basic structure of work was the magnitude of the force that you apply multiplied by the displacement. So now I'm going to use the displacement d. This is like our delta x. And then it was multiplied by the cos of an angle. Now, the cos of an angle is because of the fact that these two are vectors, okay, that we have. So we want to be able to ask, okay, what was the angle in between there? And we take the cos of that. I'll put up a link if you forgot about work. I'm going to assume, okay, that if you're studying this, you've already studied work in the past. Well, the angle within here, the displacement and the force, well, the angle is 0. So therefore, this is just equal to 1. And all I have for work is just that my force and my displacement. That's what I have. But if you have been given a graph of the displacement and the force that follows, then recall that what you can do is you can find the area under the curve to find the work. So for instance, if I would take this and I would want to find what the area under the curve is, so that's this right here, that is going to give me, or this right here, that will be giving me what is the amount of work that the spring would do. So therefore, if you're holding the spring, okay, and it's not coiled back, you have now stored energy in the spring. That stored energy is the elastic energy. If you let it go, obviously it starts to move. So whatever mass or something that you have attached is going to gain kinetic energy, and it's going to transfer from the potential energy, which is elastic, to kinetic energy in terms of the motion. If there's nothing else, like frictions, well, then those are the only two that play a role. So therefore, it will just transfer from potential, elastic energy, to kinetic energy, and then back and forth, right? So it's going to pick up speed, okay, and then it's going to slow down, and then it's going to go back and forth, right? So the spring will just coil back and forth if it was just transferring energy, if there was no damping or kind of losses due to friction. So now coming back to work, well, if you look at this and you want to be able to calculate what that area under the curve is, now we're going to take the positive value within here. So notice it's a triangle. Well, we know an area of a triangle, which is 1/2 base times height. Well, this is going to be the base itself. Okay, so it is, so that would have been this base right here. So that's our base from here to here. I'm going to take that base, and I'm going to take this as my height. So it's kind of like a flipped triangle. And in that instance, so what we would have in here is our base is just delta x. Okay, so that's our base. And now our height, okay, which is the spring, right? So this is the force of the spring. So this is multiplied by, this is going to be the force of the spring. I'll just designate it with an S right here. So that would have been this value. Now, of course, it would have been negative on this side, but I'll just keep it as positive for the moment. Now, this right here, by Hooke's law, is just simply negative K times delta X, and notice what happens. So what you will have is you're going to have 1/2 this multiplied by, and that negative, again, I'm going to just drop it because we're interested in, so negative just will tell us, okay, if it is stored or not in terms of energy. So this would have been times X, okay, so sorry, times K delta X. This is from Hooke's law right here. And if you simplify this, this indeed becomes our amount of energy, elastic energy, so you can put E or a little p for potential, where our equation is coming from. And of course, you can do that on the other side with the other triangle, and that other triangle is also going to give us, 1/2. So it just depends where you are located, and you can do that for any point. So if it was right here and this is your delta X, this would have been a smaller triangle, but that's why I am just inputting in here. So this delta X just means where are you, right, with regards to that. And if you want to recall, so areas under the curve for finding work, I'll put up a link up above there as well in case you have forgotten about that. So there you have it. So that's the elastic potential energy. So it is related towards Hooke's law. And now the final item, well, what about this simple harmonic motion, right? So what exactly is this simple harmonic motion, and how does it relate back to this elastic potential energy that we just mentioned? So once again, if I take this spring, so I'm going to take this and copy it. So let's do that. Let's bring it back down. And now we're assuming that it's ideal. Let's assume that there is no losses in terms of friction. So there's no transfer into thermal energy or heat, okay, that the actual energy will take on. So if you take this and you now stretch it out, right? So if you stretch this out, okay, so it's going to get to a certain point. Now, if you let it go, in the beginning, it will have elastic energy, right? So it has a certain amount of elastic energy. As you let it go, that elastic energy now will start to transfer into kinetic energy. And that kinetic energy is going to take it and move it so far. And then it's again going to take this and it's going to start to release, and it's going to go back in all the way as you go through, and then it will pass this point, okay, and continue. Because at this point, right, there is no more elastic potential energy. So because the spring is at its resting position, right, so this is the actual position that you have, so that means all of the energy that you coiled up into here and you let this go, so it transfers into kinetic energy. So this starts to move. So initially it starts slowly, but it has the highest acceleration, right? So it starts to accelerate, and then it's going to transfer all that elastic potential energy to kinetic energy over here. Now, so it's not going to stop because it has kinetic energy. So now it's going to start to push this, and of course, as it pushes it, now it starts to compress the spring. So now it transfers, so it starts to kind of like a dampening impact, where the kinetic energy of that mass is now being coiled back into the spring. So it's going to coil it until it releases all of its kinetic energy. And it's going to stop somewhere, so where everything goes into elastic potential energy. And of course, and then what happens? Well, the spring will fire back. So then this will now again start to move. So it's going to transfer the elastic energy back into kinetic energy. And again, it's going to go back in, and it's going to repeat this pattern, right? So it's going back and forth, back and forth. Now, in real life, of course, you have some dampening, you have some friction, so it slowly starts to whittle down and stop. But if you assume that there was no friction, right? So the surface is frictionless, the spring is frictionless, then it will just kind of go back and forth, back and forth, back and forth. And that would be considered simple harmonic motion. So simple harmonic motion is based on one thing. It's not necessarily just to do with springs. It's to do with anything in nature. But when we do say simple harmonic motion, then what we are referring to is basically, so as you're going through, so it has any type of motion that you observe where your acceleration is proportional. So we write proportional, okay? There's a symbol for it, looks like this. So the motion is, so where the acceleration is proportional to the displacement. So to the displacement. So the bigger the displacement, the greater the acceleration that it will cause, right? So it will speed up the object faster. So that is simple harmonic motion, where you, if you see that anywhere, then this is exactly what happens. Now I have simulated this. Now I've removed the spring. So I'm going to start this up within here. So this is kind of like our ball, which is released. So notice, so this is stretching it out, and then it goes back in, compresses it, stretches, and then compresses. So notice that it does stop, right? So it's basically going in, slowing down, it recoils back. And this is our simple harmonic motion, which goes back and forth. And it is periodic. So there is a period that we have. You can calculate the period for the simple harmonic motion, okay, what it is. Put up a link up above there for you, okay, in terms of the derivation. And this is for anything, and it's very nicely captured in springs because you can relate it back to springs and think about coiling and recoiling and it going back and forth, and it brings this notion where you can start thinking about waves. And waves have a period, they have a frequency that you can start to calculate. All right, so this is it for this video. I hope that you found it useful. It introduced us to elastic energy, okay, where that equation of elastic energy comes from, and then it introduced us to simple harmonic motion, okay. So these simple harmonic motions have a very periodic pattern, back and forth, back and forth. They don't have to be horizontal, they can be vertical. So in fact, you can certainly do the vertical as well within here. So I can punch that back in. So now you have two harmonic motions. And if you're doing that and you're seeing it, okay, then you can calculate periods, frequencies, and so on. Thanks for watching. Bye, everybody.